An exoplanet is a planet around a star other than our sun. But it turns out that there are about 2,000 exoplanets that are known in the universe. So there are thousands of planets known, but almost none of them are the size of the Earth. There's a strong bias to detecting larger planets, and especially large planets in short orbits. The bulk of them were detected by Kepler. It measures transits, it measures the slight dimming of a star as a planet goes across the disk of the star. You can measure those a few times and you can confirm that there's a planet there. The rest of the planets were discovered by radial velocity, which measures the motion of a star toward or away from you as it reacts to the motion of the planet in its orbit. You want to detect the light, it's very, very faint relative to the star, so there's a huge problem of glare. So the technology that I'm talking about is technology for going to space and being able to detect the light directly from a planet like the Earth, but we want to be able to put a slit across that image of the planet and then detect spectral features. Once you detect spectral features such as oxygen or water or methane, you begin to compare them to models and decide whether or not you think you're seeing signs of life. What we have to do is suppress the starlight glare around the stars so that we can see planets very close in. There are two ways to do that. One is called a coronagraph, which is an instrument inside the telescope. It blocks the starlight, but it lets the planet light through. The other is called a star shade. The idea is to put a screen out in space and block the light of the star before it has a chance to get to the telescope. A star shade is this disk. It's going to be about 34 to 40 meters in diameter. It's going to fly roughly 50,000 kilometers in front of the telescope. The idea of flying it that far away is that it has to look so small that you can see the planet just adjacent to the star. So here's an example in the lab. There's a half-scale inner disk. It's based on what's called astromesh technology, which is, if you're familiar with this SMAP spacecraft, it's the same technology, it's slightly different geometry. We made it thinner and made it more compatible with holding pedals. So there's some really neat technology development going on in this area. The other way to observe planets is through a coronagraph. And the idea now would be, instead of having a second spacecraft and waiting a week to do these observations from one to the next, you have an instrument inside the telescope and you can just point from star to star as you would for any other kind of observation. But what you've done is you've let the light into the telescope. And once you've let the light in the telescope, you've hit these imperfect optical surfaces. So now we need to have a very complex system within the telescope to control that scattered light. First thing you have to do is be able to control the wavefront. So are the high precision deformable mirrors that we use. The next thing is that you need to take this controlled wavefront and focus it onto masks, either in the pupil or in the image plane or both. Next technology is the wavefront control itself. You have to be able to sense the wavefront, you have to be able to feed that back to the deformable mirror and control it. This chronograph that's being developed at JPL now is going to fly in space roughly in the middle of the next decade in the W.R.E.R.S. mission. W.R.E.R.S. is primarily a mission to study dark energy, and there's another experiment on board to do microlensing of planets. The chronograph will also be present. It will do direct imaging, it will do spectroscopy of Jupiter size and perhaps Neptune size planets. So those are the main technologies that we're developing for this quest for looking for life around other planets.
You've seen weird, wonderful worlds in science fiction. We don't yet know what sorts of life might exist out there, but some of the planets, not unlike the ones in your favorite stories, are real. At NASA, we're studying them. They're called exoplanets. The term exoplanet means a planet outside our solar system, a planet that doesn't orbit our sun. Most orbit other stars, but some are just sunless wanderers out in the space between the stars. Now, just the fact that they orbit other stars means exoplanets are extremely far away. Most are too far to even dream of sending space probes to explore them. So we study them in other ways, like with telescopes on the ground and in space that can observe these far-off planets from right here in our solar system. Here's the thing about exoplanets. They are everywhere. In fact, from our observations so far, we know there are more planets than stars. So, there's our solar system, then there are all the billions of planetary systems in our galaxy, the Milky Way. Then there are all the billions of other galaxies. Basically, there are a lot of exoplanets out there. Each of the stars you see in the night sky is the sun for any planets that orbit around it. But not all stars are created equal. Bigger stars burn way brighter and hotter and don't last as long. Smaller, fainter stars like our sun and red dwarf stars last much longer. But even nice, cool red dwarf stars can have powerful flares that blast their planets with radiation. We're still trying to understand which kinds of stars provide long-lasting, stable conditions that could allow life a chance to take hold and evolve like it did here on Earth. Exoplanets are super hard to see, both because they're so far away and because they're so much fainter than their stars. But we've worked out some clever methods to detect them and even take pictures of some. So what can we observe? Well, for many we can determine their size, their mass, how much they weigh, and how far away from their stars they orbit. From these and a few other clues, we can infer a bunch of other qualities, like how hot or cold it might be on their surfaces, or if they even have surfaces. We can tell that some are gas giants like Jupiter, while others are like bigger, bulkier versions of Earth. For some, we can determine they have atmospheres, and even some of the gases in those atmospheres. Most exoplanets are very different from our planet. They have a lot of weird, wild variety, with gas giants much bigger than our own Jupiter, and other planets with oceans of lava, or rainy glass, or even gemstones. Funny thing is, looking at how they're arranged as families of planets, we don't see a lot of exoplanet systems that look like ours so far. Many are arranged quite differently, so we might actually be the weird ones. Some planets are closer to their stars, some are super far. Some even orbit multiple stars. Imagine having 2 or 3 suns in the sky. So why do we study exoplanets? Well, our interest in finding worlds with life on them is a big factor. We want to know more about what makes a planet a place with all the right ingredients and conditions for life, what scientists refer to as habitability. How does it happen? How common is it? We think the most life-ready planets are the ones most similar to Earth, with a range of qualities that include similar size and composition to our planet, and being at the right distance from their stars to have liquid water on the surface. These qualities are really challenging to observe from so far away, but we're working on it. Exoplanets teach us a bunch of other things too. Studying other planetary systems helps us better understand the story of our own planet family, including Earth. Scientists detected the first exoplanets in the 1990s, but now we're finding tons more, thousands so far. We're studying their atmospheres and even making weather maps for some. We're surveying exoplanets to understand all their variety. And the more we learn, the more it powers our curiosity, the more we want to explore exoplanets, planets outside our solar system.
You might think that to find another planet, you go to the telescope, you take a picture of a star, and the planet's sitting right next to it. But in fact, that's not the case. At least right now, we can't do that. So instead, we exploit the laws of physics, which tell us that as the planet is orbiting the star, it's tied by this gravitational leash, the planet also tugs on the star. It's an almost imperceptible motion, but it's one that we can measure here on Earth, on the surface, with telescopes. We actually are measuring the wobble of the star as it comes toward us and then goes away from us. And so by modeling, by taking observations night after night, sometimes for months or years, we're mapping out the orbit, one full orbit as the star goes away and then comes back toward us. And that's how we find, then we infer the presence of the planets that we can't even see. Sometimes we get lucky though. When the first planets were detected, a lot of people were skeptical about, okay, sure, they see the star wobbling, but are they really interpreting the data correctly? Are these really planets? And the one thing we knew is that eventually our technique doesn't tell us if the orbit, think of the orbit as a hula hoop, if it's sort of face on or nearly face on, or if it's edge on. And of course, if it's edge on, as the planet crosses the disk of the star, it's going to dim the starlight out. And so in 1999, we gave the predictions to our friends, astronomers who were studying the brightnesses of stars, and told them that, if this star, HD 209458, is going to transit, it will happen at exactly 7:35 tonight. And so Greg Henry at Tennessee State University was watching the star and sure enough saw the star dim ever so slightly for 3 hours while the planet passed in front of the star.